I actually just started going through the process of proving this, and it was an awful lot like stuff that we've already done in terms of taking Bellman equations minus other Bellman equations. So let me just jump to the punchline. So if you push the math all the way through, what you find is that if all the transitions and rewards are alpha close to each other, then the difference in the values that you get for following a policy is going to be no more than g over 1 minus gamma, where g is that alpha, that error amount, plus a discounted version of that error amount times the maximum reward that we get for forever. Right? So this is actually the maximum value that you can get if you get the maximum reward over and over and over and over and over again.
Okay.
So this just gives a quantity, and it has some properties that you'd expect, like the fact that if we estimate the parameters perfectly and alpha is 0, then this is 0 plus 0, and then this is 0 over 1 minus gamma, which is 0, and so the two value functions are actually identical, but they fall off from each other. So if this alpha is something not 0, some slightly bigger than 0, then these value functions are going to be off by a bit more. So ultimately what we're going to want is we want to know how accurately do we have to estimate the transition and rewards? What should alpha be so that the difference between the value that we get by running in our simulation of the model and the value that we get running in the actual MDP are really small, like epsilon close. So I think all we need to do actually is solve for alpha in terms of epsilon to be able to see how accurately we need to do our estimates to make sure that ultimately our values are going to be close.
That makes sense to me.
So this is me now solving for alpha, and we end up with this expression here, which says that we need to take the epsilon that we want, how close we want the values to be, and then transform it in various ways, actually make it a heck of a lot smaller. And that gives us how accurate we need the estimates of the transitions and rewards to be so that we know that we're going to be that close in terms of the value.
Sure, that's intuitively obvious, even to the most casual observer.
Well, okay, you're probably being sarcastic.
Possibly.
So it's maybe not completely obvious, but I did algebra here, so it's not deep, but it's not intuitively obvious to me why it should have exactly this form. In fact, usually, I don't know, epsilons are like 1 over. Oh, but I guess we're trying to define a quantity alpha, which is like an epsilon quantity. So it wouldn't make it sense for it to be a giant number. It should be a tiny, tiny number. But yeah, no, you're right. It's not completely obvious. But the point that I want to make with this is they're polynomially related to each other, right? So if we have Rmax and 1 over 1 minus gamma and 1 over epsilon, then the kind of alpha that we get out is going to be polynomially related to the other things.
Okay.
So that's reassuring. I mean, if you actually work out what these numbers are, they're pretty scary. But we're trying not to let ourselves be scared of that. The important thing, though, is that alpha is not really a parameter of Rmax, the Rmax algorithm, right? What was the parameter that we had when we talked about the algorithm?
Sí.
Excelente.
Buenísimo.
So that is to say, what we want is a parameter that says how many times do we have to try a state-action pair before we are confident that our estimate of that transition probability is better than alpha. So how are we going to get that last piece? How are we going to turn alpha into C?
More algebra?
Yeah, but specifically there's bounds that come into play here. So now we've actually turned it into the same kind of problem as the bandit problems that we were talking about, right? That we need to know how many times do you pull a bandit arm before your estimate in the mean is sufficiently close. And that was the Hufting bound.
Right. You did say we were going to use Hufting bounds.
Yeah. And the union bound.
Oh, yeah.
We want to simultaneously make this alpha close estimate hold across all state action pairs. So we need to make the C big enough so that the probability that it fails in any one of them is sufficiently small. But it really is exactly the same argument that we did when we were talking about bandits.
Okay. And sure. So every state action pair is like a bandit, and you have to pull it a certain number of times.
It's like an estimate of an arm, right? And we need all the arm estimates to be accurate if we want the arm that we eventually pick to be nearly optimal.
Right. Okay. No, that makes that, I can see the analogy. I can see the metaphor. I can see the simile.
All right, perfect. So, okay, there's one more piece to this story, and then I think we're done with exploration.
Hey, we'd be done exploring exploration. That sounded sort of sad.